The energy stored in the spring when it is stretched or compressed, that energy is called as elastic potential energy. A is a point at which another end of the spring is attached. F is the applied force, and there is a force which associated with the spring, and that is Fs, which is nothing but the spring force. The work done is nothing but the product of force and displacement. So F is the force applied to get a displacement of dx. So dw is a small work done which is equal to F into dx. Hello everyone, welcome to session 2 of chapter 6, Work, Energy and Power. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. So in the previous session, that is in our session 1, we had a discussion about the basics of work, energy, the potential energy, kinetic energy, conservation of energy, the mechanical energy, differences between the conservative and non-conservative forces. So in today's session, we are going to discuss about few more interesting concepts. Let us study with the potential energy that associate in a spring. So we will call it as elastic potential energy. We know the types of potential energies, that is elastic potential energy, gravitational potential energy as well as electrostatic potential energy. So here we are discussing about elastic potential energy. So what is elastic potential energy? It is nothing but the energy possessed by the body due to its configuration. How to understand this? What is the best example to understand this elastic potential energy? And the example for which is a wound spring in the clock can possess elastic potential energy, as well as a stretched bow. A stretched bow can possess elastic potential energy. So basically we can say that the energy stored in the spring when it is stretched or compressed, that energy is called as elastic potential energy. So the energy associated with the spring when it gets stretches or compressed is nothing but the elastic potential energy. So now let us write an expression for potential energy of a spring. So here I have considered a spring. So you can observe O here. It is nothing but the point at which one end of the spring is attached, the other end of spring is attached to a rigid body, and I'll call it as A. So after I apply some force in this direction, what happens? We can observe the spring gets stretched. So here initially it was at this position, and after the force is applied, it stretched up to a distance x. So that is what we have explained here. A is a point at which another end of the spring is attached. F is the applied force, and there is a force which associated with the spring, and that is Fs, which is nothing but the spring force. Here x is the stretched distance of the spring after the application of force. So here we have to apply some force to stretch the string, which means the force is applied to get some displacement, which is nothing but the work done. So the work done in stretching the spring through a distance dx is given by dw is equal to F into dx, because we know that the work done is nothing but the product of force and displacement. So F is the force applied to get a displacement of dx. So dw is a small work done which is equal to F into dx. So here we have to explain the terms in writing any of the expressions. So F is nothing but the applied force. So work done in stretching the spring from 0 to a distance of x. So the limits from 0 to a distance of x, we have to calculate the total work done. How to calculate the total work done? By integrating dw. So integrating means summing up all the work done, small work done, dw terms. So from what limit to what limit we have to integrate? From x is equal to 0, from 0 displacement to the displacement x. So from 0 to a displacement x, we have to calculate the total work done, and hence w is equal to integration of dw from limits 0 to x. Now we have to substitute dw by F into dx, and hence we get w is equal to limits 0 to x integral of F into dx. Here F is nothing but the applied force. So applied force is nothing but the spring force, and spring force is given by K into x. So we will get w is equal to 0 to x, the limits 0 to x in the place of f. So hence w is equal to integral of 0 to x in the place of f. I am substituting kx. So kx into dx, where k is a force constant and we have to take it out in integration. We cannot integrate a constant k, so you have to take it out and you remain with x, integral of 0 to x into dx. We know generally integration of x dx is equal to x to the power n plus 1 divided by n plus 1, or we can also say integral of x power n dx is nothing but x to the power n plus 1 divided by n plus 1. So we have x to the power 1 here in our expression. So we get integral of x power 1 dx is nothing but x to the power 1 plus 1 divided by 1 plus 1, and hence it is x to the power 2 divided by 2, and hence we get w is equal to k into x square divided by 2. We have to apply the limits now to the variable, and the limits are 0 and x. So while applying limit, we all know that upper limit minus lower limit. So in the place of this variable, I am substituting the upper limit first, and hence it is x. The upper limit is x only. So we are getting x square divided by 2 minus, in the place of variable, we have to substitute the lower limit. So it is 0 divided by 2. So 0 by anything is 0 and we remain with x square divided by 2. So w is equal to k into x square divided by 2 is our expression after this simplification, and we can write this as w is equal to, taking 1 by 2 outside, k into x square. So this is the total work done in the spring which is stored in the spring, and this work done is stored in the spring in the form of potential energy, and the expression for potential energy is given by half kx square. So let us now move on to our another important concept of this chapter, that is power. So what is power? How to define this power? We can define this in different ways. It is nothing but the rate of doing work. Rate is nothing but time concept. So the rate of doing work is also power, or it is also defined as the ratio of work done and the time taken. So the expression for power is given by work done divided by time taken, or it can be written as simply P is equal to W divided by T. So what is the SI unit of this power? The SI unit of power is watt, and the symbol is W. So this is very important in 1 mark question. The SI unit of power is watt. Symbolically we can represent watt with letter W. So now let us define 1 watt. How to define 1 watt? Now we all know power is equal to work done divided by time. So the unit of power is watt. So if this value of power must be equal to 1, what we have to take the values of work done and time? The work done must be 1 and time must be 1. So work done must be 1 joule and time must be 1 seconds. If these two values are unit values, we will get power as 1 watt. So let us define that 1 watt considering the relation P is equal to W by T. If work done is 1 joule and time taken to do that work is 1 second, then the power we can say it as 1 watt. So it is said to be 1 watt when 1 joule of work is done in 1 second. Important 1 mark question again. So we can even prove this as a vector product of force and velocity. How? So power is equal to work done divided by time. We know work done is nothing but Fx cos theta. Since we have considered dot product between two vectors, that is force into displacement, we get Fx cos theta divided by time. So we know Fx cos theta divided by time. But what is x divided by t? That is displacement divided by time. It is nothing but velocity. So replacing these two by a term v, we get P is equal to F into v cos theta. So we know that when there is a dot product between two vectors, that is f and v, we can represent that in terms of cos theta, and here we have f v cos theta, and hence we can write it as P is equal to vector f dot vector v. Hence it will give us the solution, that is fv cos theta. So henceforth we can show power is nothing but the dot product or the scalar product of two vectors, that is force and velocity. So next we are moving on to the concept collision. So what do you mean by collision? Generally, when we can say collision happens, collision means what? So collision between two bodies is said to occur when they actually strike against each other, when they actually meet each other with a certain force. When two bodies physically strike against each other, we can say the collision is occur. So collision is nothing but the path of motion of one body is affected by the other body. When one body is moving in one direction, if another body come and hits it or strike this other body, so it will deviate from its position. So the change, the path of motion of one body is affected by another body is also due to a collision. Or we can also say that collision between two or more particles is the interaction between them for a very short interval of time. So in a very short interval of time, when one body interact with the other body, we can also say it as collision. So during this interaction, one body apply force relatively on the other body, and one body is being stronger enough to deviate the path of the other body. All these things happens in a phenomena of collision. So basically it is nothing but the physical striking or the strike between two bodies, and we will call it as collision. So collision is classified into two types basically, elastic collision and the inelastic collision. So what is elastic collision and inelastic collision? How they are different from each other? So let us now differentiate between these two. Elastic collision, in which both the momentum and the kinetic energy of bodies are conserved. So in case of elastic collision, momentum and kinetic energy are conserved. We will call such type of collisions as elastic collision. What is non-elastic collision then? So how it is different from elastic collision? In case of inelastic collision, only the momentum is conserved but not the kinetic energy. Kinetic energy differs from one point to another point in case of inelastic collision, but the momentum is conserved throughout. So in case of elastic collision, the mechanical energy is not converted into any other forms. So the mechanical energy remains constant. We cannot convert the mechanical energy from one form to another form in case of elastic collision. But in case of inelastic collision, the mechanical energy can be converted into another forms or different forms. Say for example, heat is dissipated in the form of energy, that in case of inelastic collision. So these are the basic two differences between elastic and inelastic collision. So in case of elastic collision, the forces involved are conservative force. We know conservative forces are nothing but the forces that depends only on the initial and final position of the bodies. It doesn't follow the path. But in case of inelastic collision, the forces involved are non-conservative. We have already studied what are conservative and non-conservative forces in the previous sessions. So in case of non-conservative forces, the work done depends not only on the initial and final position, but it also follows the path. So in case of conservative, it is not so. It depends only on the initial and final position. So example for this elastic collision is collision between atoms, collision between any subatomic particles, and it in between two glass or steel balls. We can say that the collision happens between these materials are elastic. So the best example to understand inelastic collision is collision between a bullet and a wood. So these are the basic differences between elastic and inelastic collision. So in the next session, let us learn more concepts and derivation related to collision concept. Until then, keep learning all of you. Thank you.